Welcome to Learn with us. This is the 28th lecture of Basic Electronics.
First, we will have a quick review of your last lecture. In your previous lecture, you studied about second major classification of field effect transistors, which is MOSFETs or metal oxide semiconductor field effect transistor. In your previous lecture, you also understood two basic types of MOSFETs. First is depletion type MOSFET and second is enhancement type MOSFET. In your last lecture, you also studied about transfer characteristic curves of N-channel and P-channel depletion and enhancement type MOSFETs. What are the learning objectives of this lecture? In this lecture, you will study about N-type and P-type MOSFETs. In this lecture, you will also understand current voltage characteristic curve of MOSFETs, and you will also solve some examples related to MOSFETs. Now we will talk about P-type and N-type MOSFETs. P-type and N-type MOSFETs are complementary in their properties. N-MOSFET conducts for positive gate voltage, whereas P-MOSFET requires negative gate voltage for conduction. In N-type MOSFET, electrons are responsible for the flow of current, whereas in P-type MOSFET, holes are responsible for current flow. Now we will talk about effective and threshold voltages. Effective voltage is a point at which the value of gate to source voltage is sufficient enough for a number of electrons to accumulate in the region under the gate called as channel. Threshold voltage is the minimum voltage which is required to induce a channel. This threshold voltage is positive for N-type field effect transistors and it is negative for P-type field effect transistors. More gate voltage will cause increase in electrons in the channels. As a result, charge density will also increase. It means charge density is directly proportional to gate to source voltage minus threshold voltage, or we can say that charge density is directly proportional to effective voltage. It means effective voltage is equal to gate to source voltage minus threshold voltage. Okay. Now what is pinch off voltage Vp? Pinch off voltage is a point at which gate to drain voltage is equal to threshold voltage. Now we can write this gate to drain voltage like this. Gate voltage minus drain voltage is equal to threshold voltage, or we can write it like this. VGS minus VDS is equal to threshold voltage. Now if we rearrange this equation, we get drain to source voltage is equal to gate to source voltage minus threshold voltage. From our previous slide, we know that effective voltage is equal to gate to source voltage minus threshold voltage. Now this is equation A. It means this equation A can be written as gate to source voltage is equal to effective voltage. Okay, so this is your pinch off voltage. Now we will understand current voltage characteristic curve of MOSFETs. In this case, the variable of y-axis is drain current and the variable of x-axis is drain to source voltage. Here the curve looks like this, okay, where the region from this point to this point is triode region. This constant region is called saturation region, and here on this x-axis we have third region, which is cutoff region, where drain current is 0. It means MOSFET has three regions of operation. First region is cutoff, second region is saturation region, and third region is triode region. In cutoff and saturation regions, MOSFET acts as a switch, whereas in triode region, MOSFET acts as an amplifier. Now look at this curve. Here this point is Vp. It means it is pinch off voltage. At which gate to drain voltage is equal to threshold voltage. As you can see, before this point pinch off voltage, transistor acts as linear resistor in triode region. Okay. Now we will understand voltages in regions. First we'll talk about cutoff region. In cutoff region, threshold voltage is greater than gate to source voltage. Now what about triode region? In triode region, gate to source voltage is greater than equal to threshold voltage, and here gate to drain voltage is greater than threshold voltage. Now we can write it like this: VGS minus VDS is greater than threshold voltage. It can be written as VGS is greater than threshold voltage plus drain to source voltage, or we can write this equation like this, and if we rearrange this equation, it becomes like this. Now we know that effective voltage is equal to gate to source voltage minus threshold voltage. It means here this drain to source voltage is less than effective voltage in triode region. Okay. Now we will talk about voltages in saturation region. In saturation region, gate to source voltage is greater than equal to threshold voltage, and here gate to drain voltage is less than threshold voltage. Now we can write this gate to drain voltage like this. Now if we rearrange this equation, we get gate to source voltage is less than threshold voltage plus drain to source voltage, or we can write it like this. Now if we rearrange this equation, we get drain to source voltage, it is greater than threshold voltage minus plus gate to source voltage, or here we can write it like this, is greater than gate to source voltage minus this threshold voltage. Now we know that this term is equal to effective voltage. It means here in this saturation region, drain to source voltage is greater than effective voltage. Okay. Now look at this curve. In this triode region, this drain to source voltage is less than effective voltage, whereas in this saturation region, this drain to source voltage is greater than effective voltage. Okay, so these are the voltages in all these three regions in case of MOSFETs. Now we will understand currents in regions. We know that in all field effect transistors, gate current is equal to 0 and drain current is equal to source current. Now first we will talk about currents in cutoff region. As you can see here, in cutoff region, drain current is 0. It means here source current will also be 0. Now what about triode region? The equation of drain current in this region is this. Now neglecting this higher order term, we get this equation. Now we know that this gate to source voltage minus threshold voltage is effective voltage. Okay, so we can write it like this. Now here this is transconductance parameter. The equation of transconductance parameter is this, where this term is mobility of electrons. This term is capacitance of oxide layer, and this ratio is transistor aspect ratio, where this is width and this is length. Okay, now this capacitance is equal to this equation, where this is permittivity of silicon dioxide, and this term is oxide thickness. Okay, now what about the equation of drain current in saturation region? The equation is this: gate to source voltage minus threshold voltage whole square. Now, as you can see here, this drain current is independent of drain to source voltage here. Okay, so these are the currents in all three regions of MOSFETs. Now, what is the importance of MOSFETs? Here we'll talk about some important points. MOSFETs have low power consumption for effective operation. They have tremendous switching speed. Their size is very small. They make all ramps of the world. They have ease of fabrication. It means their terminals are interchangeable due to flexibility. For circuit analysis, I'll be using this symbol for MOSFETs, where this terminal is gate, this is drain, this is source, and the arrow will be here for N-type MOSFET, and this is the direction of drain current here. Now what about P-type MOSFET? The symbol for P-type MOSFET will be like this, where this terminal is gate, this is source, this is drain, so arrow will be here. This is the symbol of P-type MOSFET. Here in this N MOSFET, drain voltage is greater than source voltage, whereas in case of P MOSFET, source voltage is greater than drain voltage. Okay, here positive gate voltage is applied and here negative gate voltage is applied. Okay, now look at this example. If you have a circuit like this, arrow is here, it means it is N-type MOSFET. So this terminal is drain. For suppose here VDD is 5 volts, here we have VSS which is minus 5 volts, here we have RD, here we have RS, and here this gate is grounded. Okay, now if drain voltage is 1 volt and drain current is 0.3 milliamperes, this is the direction of drain current. Okay, and threshold voltage is 3 volts, and length is 9 micrometer, and width is 400 micrometer. Here gate voltage is 0 volts, and we know that gate current is 0 amperes, and here this term is equal to 20 microampere per volt square. Okay, so how you are going to start your analysis? First we will find source current. We know that in all field effect transistors gate current is 0. It means here drain current is equal to source current. As you can see here, drain current is 0.3 milliamperes. It means here source current will also be 0.3 milliamperes. Okay. Now we will find mode of operation here. You know that in saturation region, gate to drain voltage is less than threshold voltage. Here this gate to drain voltage is equal to gate voltage minus drain voltage, and here we have threshold voltage. Here this gate voltage is 0, this drain voltage is 1 volt, and this threshold voltage is 3 volts. It means here this condition is satisfied. It means this transistor is in saturation mode. Now we know that in saturation region the equation of drain current is this. Okay, now here this value of gate to source voltage is unknown, and for this first we have to find the value of K. We know that the equation of K is this. Here this term is equal to 20 microamperes per volt square. This width is 400 micrometer, and this length is 9 micrometer. After solving this, we will get 4.44 into 10 raised to the power minus 4 amperes per volt square. So this is the value of K here. Now here we are finding gate to source voltage. Now we will put all the values in the equation of drain current. So we have 0.3 into 10 raised to the power minus 3 amperes is equal to 4.44 into 10 raised to the power minus 4 amperes per volt square. And here we have gate to source voltage minus 3 whole square. Okay, now if we rearrange this equation, we get 0.3 into 10 raised to the power minus 3 amperes divided by 4.44 into 10 raised to the power minus 4 amperes per volt square. This ampere is going to cancel this ampere here, and here we have VGS minus 3 whole square. Okay, now we take square root on both sides. We have this. Here after solving this, you will get 0.675 volt square, and here we have VGS minus 3. Now if we solve this, we get 0.82 volts, and here we have gate to source voltage minus 3. If we rearrange this equation, we get gate to source voltage is equal to 3 plus 0.82 volts. This is volts, volts, and volts. It means this gate to source voltage is equal to 3.82 volts. Okay, now we will find source voltage. We know that gate to source voltage is equal to gate voltage minus source voltage. It means here source voltage is equal to gate voltage minus gate to source voltage. We know that gate voltage is 0 and gate to source voltage is 3.82 volts. It means here source voltage is equal to minus 3.82 volts. Okay. Now what about drain resistor RD? Here the equation of RD will be VDD minus VD divided by ID. Okay, here we know that this VDD is 5 and this VD is 1 and ID is 0.3 milliamperes. After solving this, you will get 13.3 kilo ohms. Okay, now what about RS? The equation of RS will be Vs minus VSS divided by Is. Here we know that Vs is minus 3.82 volts and here we have minus 5 and we know that Is is 0.3 milliamperes. After solving this, you will get 3.93 kilo ohms. Okay, so this is your answer. This is how you are going to analyze these circuits. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is N-type MOSFET. Here this terminal is drain and here we have VDD and for suppose it is 10 volts. Here we have RD and here we have VD, here we have VG and here we have Vs and it is 0 because here this source is grounded and as you can see here this gate voltage is equal to drain voltage. Okay, now if drain current is 0.4 milliamperes, threshold voltage is 2 volts. We know that gate current is 0 amperes and here length is 10 micrometer, width is 100 micrometer and this term is equal to 20 microamperes per volt square. Okay, and we know that here Vs is 0 and you have to find the value of drain voltage here. So how you are going to start your analysis? First we will find mode of operation. We know that in saturation mode VGD is less than VT. Here this VGD can be written as VG minus VD, which is less than threshold voltage. Here we know that gate voltage is equal to drain voltage. It means here this is VD and here this is VD. It is less than threshold voltage. This is 0 and here we have 2. Okay, it means here this condition is satisfied. It means this transistor is in saturation mode. Okay, Now we will find gate to source voltage. We know that in saturation region the equation of drain current is this minus Vt whole square. Here we know that this K is equal to half mu n cox W divided by L, and here we have Vgs minus Vt whole square. This is ID. Now if we put values here in this equation, this ID is 0.4 milliamperes, and here we have half 20 microamperes per whole square. This width is 100 micrometer and length is 10 micrometer. Here we have VGS, and here this threshold voltage is 2 volts and it is whole square. Okay, and after solving this term you get 100 into 10 raised to the power minus 6 amperes per whole square, and here we have VGS minus 2 whole square. Okay, now if we rearrange this equation, we get 0.4 into 10 raised to the minus 3 amperes divided by 100 into 10 raised to the power minus 6 amperes per whole square, and here we have VGS minus 2 volts whole square. Now this ampere is going to cancel this ampere, and if we solve this we get 4 volts square. Now we take square root on both sides, and here we have VGS minus 2 volts, here we have 2 volts, and here we have VGS minus 2 volts. It means this gate to source voltage is equal to 2 volts plus 2 volts, and it is equal to 4 volts. So this is gate to source voltage here. Now we know that gate to source voltage is equal to gate voltage minus source voltage. We know that here this gate voltage is equal to drain voltage. It means this equation can be written as Vd minus Vs. Here we know that this gate to source voltage is 4 volts, this drain voltage is unknown, and this source voltage is 0 volts. It means here this drain voltage is 4 volts. Okay, now if you want to find drain resistor here, the equation will be VDD minus VD divided by ID. Here we know that VDD is 10 volts and VD is 4 volts, and this ID is 0.4 milliamperes. After solving this, you will get 15 kilo ohms. Okay, so this is your answer. Okay, that's all for today. Now, what are the key takeaways of this lecture? In this lecture, you studied about current voltage characteristic curve of MOSFET. You studied that there are three regions of operation in MOSFET. First region is cutoff region, second region is triode region, and third region is switch off region. In this lecture, you understood voltages in all these three regions. You also studied about currents in all these three regions of MOSFETs. In this lecture, you also solved some examples related to MOSFETs.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.